Have you ever looked up at the night sky and marveled at the tiny dots silently moving across the stars? Those dots are satellites, and they play a crucial role in our daily lives, from providing GPS navigation to weather forecasting and global communications. But how do these technological marvels manage to stay in orbit without plummeting back to Earth? The answer lies in a fascinating dance between gravity and velocity. Join us as we unravel the science behind this incredible phenomenon and discover the secrets that keep satellites orbiting our planet. Key concepts: gravity. Gravity is the force that pulls objects toward Earth, keeping us grounded and giving weight to everything around us. This same force acts on satellites, pulling them toward the Earth. However, satellites don't crash into the Earth because they are moving forward at a high speed. This forward motion, combined with the gravitational pull, creates a delicate balance that keeps the satellite in a stable orbit. Gravity acts as a central force, continually pulling the satellite inward while its forward momentum tries to send it off into space. The result is a curved trajectory around the Earth, which we call an orbit, inertia and forward velocity. When a satellite is launched, it is given a significant amount of forward velocity. This high speed is crucial because it creates inertia, the tendency of the satellite to keep moving in a straight line. In the absence of gravity, this inertia would cause the satellite to drift off into space. However, gravity continuously pulls the satellite towards the Earth, bending its path into a circular or elliptical orbit. This interplay between inertia and gravity ensures that the satellite does not escape into space or fall back to Earth, but instead follows a consistent orbital path around the planet. The balance. The key to a satellite's orbit is achieving a perfect balance between its forward velocity and the pull of Earth's gravity. Imagine swinging a ball on a string around your head. The ball wants to fly off in a straight line due to its inertia, but the string pulls it inward, creating a circular motion. Similarly, a satellite is constantly falling towards Earth due to gravity, but its high speed ensures it keeps moving forward, resulting in an orbit. This balance ensures that satellites stay in a stable path around the planet without drifting off into space or plummeting to the ground. If the satellite's speed is too slow, gravity will pull it back to Earth. If it's too fast, it will escape Earth's gravitational pull and drift off into space. Steps to achieve orbit. Launch. The journey of a satellite begins with a powerful rocket launch. The rocket propels the satellite beyond Earth's atmosphere, where the air is thin and resistance is minimal. This initial phase is critical to escaping the dense atmospheric drag and reaching a region where the satellite can maneuver more freely. Rockets are designed to provide the necessary thrust to overcome Earth's gravitational pull and achieve the high speeds required for orbital insertion. The launch phase involves precise calculations and engineering to ensure the satellite reaches the desired altitude and speed. Acceleration. Once above the atmosphere, the rocket boosts the satellite to a high velocity. For low Earth orbit, this speed is around 28,000 kilometers per hour, 17,500 miles per hour. This rapid acceleration is necessary to achieve the tangential velocity that keeps the satellite in orbit. Without this speed, the satellite would not have enough momentum to counteract the pull of gravity. The acceleration phase ensures the satellite gains the necessary kinetic energy to maintain its orbit and provides the foundation for its continued motion around the Earth. Attaining the orbit. The satellite is released at a precise altitude and speed. This careful placement ensures that the satellite's velocity creates a balance with gravitational pull. Engineers meticulously calculate the necessary speed and position to achieve the desired orbit, whether it's a low Earth orbit for communication satellites or a higher geostationary orbit for weather monitoring. Achieving the correct orbit involves a combination of rocket science and physics, ensuring the satellite maintains a stable path around the Earth without needing constant adjustments. Types of orbits: low Earth orbit, LEO. Satellites in low Earth orbit, LEO, positioned between 200 to 2,000 kilometers, 124 to 1,243 miles above the surface, offer detailed imaging, rapid communication, and frequent orbiting, making them ideal for Earth observation and certain communication tasks. Their proximity allows for high-resolution images and real-time data as they complete multiple orbits daily. However, the lower altitude results in increased atmospheric drag, necessitating periodic adjustments to sustain their orbit. This proximity to Earth enables LEO satellites to deliver detailed and timely information, enhancing their utility for monitoring environmental changes, disaster management, and providing internet services to remote areas. Despite the need for frequent maintenance, their advantages make them crucial for many modern technological applications. Geostationary orbit, GEO. In GEO, satellites orbit at about 35,786 kilometers, 22,236 miles above the equator. Here, they match Earth's rotation, appearing stationary relative to the ground. This makes them perfect for broadcasting and weather satellites, providing consistent coverage over specific areas without the need for constant repositioning. Satellites in GEO are ideal for telecommunications, television broadcasting, and weather forecasting, offering uninterrupted service and wide coverage areas. Their high altitude ensures minimal atmospheric drag, resulting in stable, long-term orbits. Polar orbit. Satellites in polar orbits travel over the Earth's poles, allowing them to scan the entire globe as the planet rotates beneath them. This orbit is especially useful for environmental monitoring, weather forecasting, and global mapping. Polar orbiting satellites provide critical data for climate studies, natural disaster monitoring, and global navigation systems. Their ability to cover the entire Earth's surface makes them invaluable for scientific research and environmental observation. These satellites offer comprehensive data collection, enabling detailed analysis of global weather patterns, environmental changes, and geographic features. Their contributions are essential for understanding and responding to climate change, predicting natural disasters, and enhancing navigation and communication systems. Polar orbits ensure that no part of the Earth is left unobserved, making these satellites crucial for a wide range of applications. Maintaining the orbit, orbital adjustments. Satellites maintain precise orbits using small thrusters that make minor adjustments to correct deviations caused by gravitational influences from the Moon, the Sun, and atmospheric drag in lower orbits. These corrections ensure satellites stay on their intended paths and function effectively. Ground stations regularly monitor and control the satellite's orbit, managing these adjustments to keep it within designated parameters. This ongoing process is crucial for extending the satellite's operational life and maintaining the quality of its data and services. By continuously making these minor corrections, satellites can provide reliable performance and meet their mission objectives over extended periods. Why satellites don't fall back to Earth? Tangential velocity. The satellite's high tangential velocity is crucial. As gravity pulls the satellite towards Earth, its forward motion keeps it moving around the planet instead of crashing into it. This creates a continuous free fall where the satellite is always falling towards Earth but keeps missing it due to its high speed. This delicate balance ensures that satellites remain in orbit, providing vital services like GPS, weather forecasting, and global communication. The concept of tangential velocity highlights the importance of speed in maintaining orbital stability, allowing satellites to function effectively and deliver essential services to people around the world. Thank you for watching. If you enjoyed this explanation, please like, share, and subscribe to Me Explained. Hit the bell icon for more informative content. See you next time.